Hello, this is Lab 3 for Physics 2211, Section M at Georgia Tech, covering the nature of a star orbiting a black hole. In this experiment, we were given the mass of a star orbiting a black hole, and each student was given a different trajectory that the star followed. By changing certain aspects of the glow script code, we are able to use calculations to find the net force acting on the star at different time steps in the orbit. Because the end goal of the lab or experiment is to determine the mass of the black hole, the net force acting on the star is necessary to use the gravitational force equation to calculate the mass of the black hole. Before continuing on, we care about this because not only does everything in our life generally revolve around gravity, but we can also use this information to understand the Earth's orbit around the Sun, assuming we consider the Sun to be a non-moving object. Or we can use it to understand how our solar system and galaxy revolves around its own black hole, and whether or not we need to be afraid of something in the future. Going back to the experiment, let me elaborate on why we can use the orbit of the star, the amount of time it takes, and the star's mass to determine the net force. As we know, the universal gravitational force equation is the force equal to the gravitational constant, 6.7 times 10 to the negative 11th, times the mass of the two objects, in this case the black hole, which the mass is unknown as of now, and the star, which is 2 times 10 to the 30th kilograms, divided by the distance between them squared, or r squared. When we look at this equation, because the only unknown, assuming we calculate the net force, is the mass of the black hole, we can rearrange it to solve for its mass. Thus, we have to find the net force at different locations in its orbit. Back to solving for the net force at different locations, we know net force on an object to also be equal to the change in momentum over the change in time. Because we know this, having the distance of the time steps to be 1 day, or 86,400 seconds, we can use the position coordinates and the mass to find the change in momentum, or the net force. By doing this, we will originally need to find the change in position between 2 points, or r2 minus r1 on the orbit, divided by 86,400 seconds to get the velocity of the star in meters per second. Follow this by multiplying it by the mass to get the momentum, and then finally, by finding the star's momentum at different locations, we can use the aspect of P2 minus P1 divided by, once again, 86,400 seconds, which will give us the net force acting on the star over that period of time. At that point, we can simply rearrange the gravitational force equation to isolate the mass of the black hole, which we find to be around 9.3 times 10 to the 33rd kilograms. Going into the what does it mean and what if sections of this lab, when we look at the force of gravity from the black hole on the star, the force can be split into two parts, which are the perpendicular and parallel components of the force. In the star's orbit, the parallel component of the force is the aspect that is solely influencing the speed of the star, specifically in regards to speeding up or slowing it down. Conversely, the perpendicular component of the force influences the aspect of turning for the star. To put into visual terms, the parallel component is always in the direction of the instantaneous velocity, or parallel to its instant motion, while the perpendicular component is always pointing towards its source of gravity, in this case the black hole, which is perpendicular to the instantaneous velocity or momentum. When looking how those components can differ from force to change in momentum, one is derived from the other. Here it is change in momentum. The change in momentum over time is something we can directly see, as the star is moving a certain distance over a certain time, all while holding a mass. However, the only reason this momentum is occurring is due to the force that is causing the change in position, which is why the change in momentum is derived. The force causes the change in momentum. However, we use that change in momentum to calculate in the force that in turn caused its change in position. Yes, I understand it sounds like a loop, but it is accurate. Lastly, if there was a new black hole that replaced the old one, but the motion of the star stayed the same, there would be no way to calculate a different mass. To explain this, because we used the different position points and the amount of time it took to calculate the net force, the same orbit would produce the same net force. Thus, when we in turn use that to calculate the mass of the new black hole, the same net force would produce the same mass no matter how we calculated it. That is all for this lab. Thank you.